Foundations of Amateur Radio. In 2016, Daniel, Echo Alpha 4 Golf Papa Zulu, documented how to discover the weakest signal that could be decoded using several weak signal modes, including WSPR, or Weak Signal Propagation Reporter. This is an interesting question because, as you might recall, I've been experimenting with very weak signals coming from my shack. To date, my 20 milliwatts has been heard over 13,000 kilometers away. When you tune to a weak station, you'll often hear both the station or desired signal as well as interference or background noise. The stronger the signal, the less noise you perceive. The weaker the signal, the more noise. You can express the relationship between the power of these two, the signal and the noise, as a ratio. If the power levels are the same, the so-called signal-to-noise ratio, or SNR, is 1:1. A higher ratio, like 2:1, indicates that the power of the signal is higher than the noise, and a lower ratio, like 1:2, indicates that the signal is lower than the noise. If you express this ratio in decibels, you'll end up with positive numbers where the signal is stronger than the noise, and negative numbers where the signal is weaker than the noise, and 0 when they're the same. If I tell you that the signal report for my WSPR decode from Denmark was -28 dB, it means that the noise was much stronger than the signal. For today, I'm going to leave alone just how WSPR can report a negative signal-to-noise ratio and still successfully decode the signal, even though the signal appears to be buried in the noise. That said, in this experiment, we are trying to learn something else. Using the technique detailed by Daniel, we test using different, known signal-to-noise ratios to discover at what point the WSPR decoding process breaks down. This might help me understand if I can reduce my beacon output power even further and still anticipate a good chance of being decoded successfully. To conduct his experiment, Daniel used the then current version of WSJTX, version 1.7.0, release candidate 1. And I'm using the current version today, 2.6.0 release candidate 5, to repeat those tests. You might ask why I'm not taking Daniel's word for it and just using his findings. The process to decode a WSPR signal is all software and can be improved with better methodologies and algorithms. It's not unreasonable to think that in the years since Daniel's experiments, things have changed, hopefully improved. So, how does this work? If you generate and attempt to decode 100 different files, you can use the number of times that you count your call sign in the decode list as a percentage of success. If all of your files decode properly, the decode percentage is 100%. If only half of them are decoded successfully, it's 50%, and so on. Similarly, if a different call sign, locator, or signal power is decoded, you can count those as a percentage of false decodes. This is important because noise coming from the ionosphere can corrupt any signal. I should point out that because we know in advance what the decoded signal should be, since we created the message, we can actually count the ones that don't match what we sent. In the real world, it's very hard, if not impossible, to do this unless each transmitter also starts recording their efforts, so data cleaning can be done after the fact. A false decode happens when the software decodes a message and the result is not what was sent. Due to the way that WSPR works, this is not a case of a single character error, and as a result the whole message is corrupt, wrong call sign, wrong grid square, and wrong power level. Just how prevalent this issue is has, to my knowledge, so far not been discussed. Over the past year I've been working with the entire WSPR dataset, nearly 5 billion reports, and mapping the data to explore just what's going on behind the scenes. Based on the raw data, every single grid square on the planet has been activated. Of course, this is not really the case, since there's plenty of parts on Earth where we haven't yet turned on a WSPR beacon. Back to our experiment. Two tools are used, WSPR Sim to generate an audio file and WSPR D to decode it. Both come with WSJTX, and when you build the application from source, you get them as part of the process. The generator takes several parameters, one of which is the desired signal-to-noise ratio. If you ask it for a signal-to-noise ratio of -20 dB, WSPR will generate the appropriate noise and the desired signal, combine them, and build an audio file. You can then use WSPR to decode that file. If you repeat this many times, you can end up with some data. How many times? Well, I probably went a little overboard. I generated a set for each SNR reading between 0 and minus 50 dB in 0.01 dB increments, and then generated 100 for each of those. At the point where the process broke down, I doubled the resolution further to get a better idea of what was going on. About 750,000 tests. It took a while. What did I learn from this? First of all, false decodes happen at every signal level. I saw the first false decode at a signal-to-noise ratio of minus 0.07 dB. This is significant because it means that even at excellent signal levels, there is a percentage of incorrect reports, which explains why I'm seeing that result in real-world data. When you start playing with really big numbers, even if the error rate is low, with enough data, it starts to matter. In my tests, I saw an error rate of 0.03%. This means that there's at least 1.5 million false decodes in the current WSPR dataset, likely more because WSPR cannot emulate the real world of ionospheric and local noise. On the flip side, I also saw an overall success rate of nearly 94%. At minus 29 dB, things start to change. Until then, the decode is 100% successful. Then it starts to decline to 0 at about minus 34 dB. Comparing Daniel's results directly, he saw 34% success at minus 30 dB. I'm seeing 95% at that same noise level. At minus 31 dB, Daniel saw 6%. I'm seeing 75%. I don't see 34% until we get down to minus 31.6 dB, and 6% at minus 32.4 dB. This indicates that the software has improved over the years. It also means that with a signal report of minus 28 dB from Denmark, I've got a few dB to play with. I've now reduced my output power by another 3 dB, making it 10 milliwatts. Point your antennas at VK6 and see what you can hear on 10 meters. I'm Ono, Victor Kilo 6, Foxtrot Lima, Alpha Bravo.